Okay, so we've just finished talking about this relationship between the first and second quadrant. So going from an acute angle to an obtuse angle. We might deal with other quadrants a little bit later and talking about them later on in this video, but we're going to mainly focus on obtuse angles through most of the work you'll be set this particular lesson. So we just have to understand that basic idea that for every angle, every acute angle, there's an obtuse angle in sine's case with the exact matching ratio, and in cos's case with the same ratio except it's negative instead of positive. Now tan's a little bit different again. Tan is also negative, so there's a matching negative ratio. Tan's a little bit different because if we go back to our triangle up the top here, because we're talking about the opposite over the adjacent, we can end up with a situation where tan doesn't have to be constrained. It doesn't have to be always less than 1 in the same way that the sine and cos ratios are always less than 1. So it can behave in different ways. I'm going to deal with that more in this next little bit. So this is going to be rather short, and I will say first up in this video, so I get it out of the way early, the questions for this particular lesson are small because there's a lot of new content going on. All right, so don't freak yourself out too much that I'm still going on with videos and you're never going to get the work done. I think there's only 3 questions set and they're relatively basic. But I just wanted you guys to get an appreciation of how these things all behave and work together. And so we've got these over the course of the 3 next pages in the theory booklet. They all look the same, and we're just going to talk about the sine and cos ratios over a full 360-degree revolution. So what I want you to do, and we're just going to do it to 1 decimal place because there's not really much point going beyond that. If we're graphing, we're not going to be able to see anything more than that. So we just start looking at filling in this table of values, and I'm not going to make you sit through me filling in the whole table of values. I will pause and fill it out, and you can fill it out yourself obviously as well. But we start with sine theta of 0, sine of 0 is 0, and we just keep going along like that, and sine of 30. So there's going to be a bit of clicking and pressing to do, is 0.5. Now if we remember what adds up with 30 to 180, oh, well, that's going to be 150. So I know without even using my calculator that that's going to be 0.5, because with sine, for every acute angle, the obtuse angle that adds up to 180 will have the same ratio. So if I do, for instance, sine of 45, I'm going to get 0.7, and I know that if I add 45 to 135, I'm going to get 180, so this one's going to be 0.7 as well. And then if we do sine of 60, that's I'll call that 0.9 in this case. And I know that 60 plus 120 equals 180, so this is going to have the exact same value. And on we go from there. And sine of 90 degrees, although not technically possible with a right angle triangle, but nonetheless, oh, what am I doing? 90 equals 90. Sine 90 is going to actually equal 1. That's as big as that can get. And well, what adds up with 0 to make 180 degrees? 180 degrees adds up with 0 to make 180 degrees. So if this is correct, sine of 180 degrees should also be 0. And look at that, it is. Now, on from here, just key in the values, but you'll find that sine will probably go negative. Now, in much the same way, we can expect the cos ratio to behave the same way. So what I want you to do just now is just ignore those questions for the time being. I'll come back and we'll deal with them in a second. But just sit there with your calculator and key in to fill out that table of values there for sine. Then fill out the table of values there for cos. And then we'll fill out the table of value there for tan. Something just to warn you about though with the table of values for tan is there's going to be a math error for some of those numbers, and we'll talk about why that is in a second. But like I said, I'll pause now, I'll fill out those table of values, and I'd like you to do the same. Okay, so I've filled in my 3 tables of values, and I've also plotted the points. So you might want to take a minute now to do that. Just pause the video. Or you can copy off my points I've plotted here. And you can see that what ends up happening when we start looking at different values of sine up to 360 is we end up, now I'm going to have to move my laptop so my head will disappear for a bit, but we'll just have to deal with that. Maybe you'll end up looking up my nose, who knows. So it ends up doing this kind of wave, and it's no fluke that it's a wave. And the reason why I say it's no fluke is this is known as a sine wave. Where does it get its name from? Well, it's the wave that a sine ratio makes. And this is what I talked about with regards to trigonometry being able to be used to solve weird problems. We started off talking about triangles, and now all of a sudden, if we graph trigonometry over a series of angles, we end up with a situation where a wave starts forming, and this wave is going to keep repeating. And so it allows us to mathematically model things that come along periodically, things like sunrise and sunset, or weather phenomena, or all sorts of things that change, and all sorts of things that change over time but don't just keep growing, they ebb and flow. And also radio waves, all those sorts of things. Communication gets a lot out of this. We need to be able to model it mathematically so we can manipulate it to be able to have television, do things like that. So that's our good friend, the sine wave. It starts at 0, goes up to 1, back down to 0, down to -1, and back up to 0 again. And you'll see that the cosine is very similar, but it's like it's off by 90 degrees. So if we draw this one in, we end up with a nice wave that looks pretty much the same as the sine wave. Whoops, that's a little bit poor there, except that it's in a different position at every given point than the sine wave, but otherwise it looks pretty similar, and it's going to continue and do the same sort of thing over time. It's going to end up sort of doing this just as the sine wave would. It's just at different values it'll be high or low. And then the final one, we'll come back and answer the questions in a minute, and the final one is the tan ratio. Now tan does something really weird. You might have picked up, and I've highlighted it here in green, you can't get an answer for the tan of 90 degrees or the tan of 270 degrees. It gives a math error. The reason why it does is, in order to do that, if we think about it logically, think about the opposite and the adjacent side, an angle of 90 degrees is going to mean that the adjacent side is equal to 0. If the adjacent side is equal to 0, then we're going to be dividing by 0, which gives us a math error. So tan of 90 is effectively the same as dividing by 0, in the same way tan of 270 is. So we end up with this function, and I'll just zoom down here, that starts off here and goes this way. And then it's going to come back in here, sort of flick around, and go that way. And then likewise here, it's going to come, and it's just going to repeat this basic pattern. It's a pretty poor line there. It's going to repeat this basic pattern every 180 degrees. It's going to create a new period of itself. So that's how the tan ratio looks. So if we go through these questions, which I'll go through as quick as I possibly can, what's the maximum value for sine theta? Well, it never gets any higher than 1. Where does the maximum occur? Well, that occurs at 90 degrees. At 90 degrees, we're up at the value of 1. What is the minimum value? Well, that's down at -1, and that occurs at 270 degrees. Where does sine theta equal 0? Well, it starts off at 0 degrees, equaling 0. Then at 180 degrees, it equals 0 again. And then it does again at 360 degrees. Not 36, 360. And then in what quadrants is the sine ratio positive? So between 0 and 180 degrees, it's positive. So it's positive here and it's positive there. But after that, it's negative for the next 180 degrees. So it's negative down here and negative down there. So we'll move on to the next one. What's the maximum value? Well, once again, that's going to be 1. And where does that occur? Well, that happens when we've got 0 degrees or 360 degrees. And the minimum value is -1, and that happens at 180 degrees, just the once on this particular graph. Where does cos theta equal 0? Well, it equals 0 at 90 and 270 degrees. So in what quadrants are we positive? So we're positive there in the first quadrant, everything is, and it's also positive there in the final quadrant, the fourth quadrant. So it's going to be positive here and positive there, making it negative, and we already knew that for obtuse angles, but for, say, our reflex angles, the next 90 degrees around it's going to be negative, and then the last 90 degrees back around to 360 is going to be positive. And then for tan, what's the maximum value of tan theta? It's actually infinite. All right, if we go just, and I'll explain that, just although we only got to 1.7, if I did tan of 89.9999 degrees, I'm going to get a really large number. So it's going to keep going, it's going to approach, it's going to keep approaching, it's going to keep expanding and almost hitting this line but never touching that line. It's going to just scoot past. So its maximum value is infinity. Where does the maximum value occur? And it's sort of just before, in this case, 90 and 270 degrees. But obviously it can't equal them. What's the minimum value? Well, that's going to be negative infinity. Once again, this line is going to keep going south, approaching that green dotted line, but never touching it. And where does that occur? Well, it's going to occur at just after, 90 degrees and 270 degrees. So to give you an example of that, if I did 90, tan of 90.001, it's going to give me a really large negative number. Okay. Where does it equal 0? In this case, it's going to be equal to 0 at 0, 180, and 360 degrees. And where is it positive? Well, they're all positive in the first quadrant. Otherwise, we'd been dealing with this with right angle triangles. But for tan, it's negative here between 90 and 180 degrees. So it's negative in that quadrant. Between 180 degrees and 270 degrees, it's positive. And then finally, it's negative in that last quadrant between 270 and 360 degrees. Okay, so I'd like you to have a go at those questions there. They're not too hard. They don't deal so much with this stuff that we've just dealt with. It's just nice to get a bit of an idea of the relationship. It's a lot more dealing with this basic relationship here that for every angle between 90 and 180 degrees, there's a matching pair between 0 and 90 degrees, and that's of the same quantity, but it might be a negative value rather than a positive value. Now you'll see I've have steered away generally from the notes in here. I would say once you've got a bit of a handle on this, then have a read of the notes. I think they're a little bit heavy to start with. So by all means, have a look at the notes now if you're comfortable with them. But if not, just get stuck into the lesson and maybe come back to the notes later and it'll all start to make a bit more sense.